All right, so for 98, it says use the zero product property to find the exact vertex of y equals x squared plus 8x plus 10. What went wrong? How could you work around the problem? So what they're asking us to do is use factoring, so the box and diamond method, to find the x-intercepts, and then from there to find our vertex. Now, by the way, just in case you don't know, because we haven't really used this word much, the vertex is just that bottom point on the U of the parabola. So like right here is our vertex. Okay, so obviously they're pointing out that something's not going to work. So when I set up the problem for box and diamond, I always put these two numbers in their correct places, set up the diamond, and I'm looking for two numbers that multiply to make 10x squared and add to make 8x. So I made a list of my possibilities off to the side here, 1 and 10, 2 and 5, -1, -10, -2, -5. And what I noticed is that none of those pairs add to make 8. So what am I supposed to do with that? Well, that means that it doesn't factor. I can't actually find those pieces that would make this box work because this doesn't factor. So it's not very helpful for us, but what that means is I can use other methods to work around this problem. So I can go to Desmos and look at the graph, and I can just get a good estimate of these x-intercepts, which are at -6.45 and -1.55. Once I've gotten those, I can use that to help me find my vertex. Or I could just look at the graph and see right there on my graph where the vertex is. Two different ways of getting to the answer of the same problem. Okay, so then 99 says I can actually take that function that we were just looking at, x squared plus 8x plus 10, and I can rewrite it in what they call graphing form. Now, graphing form has this setup where there's something in parentheses, squared, and then a number usually added or subtracted at the end. It's just kind of a handy way for us to graph because it's going to show us some important information. Now it says to find the exact x-intercepts and vertex. The convenient part about graphing form is that the vertex is always going to come from what we see here. So my vertex in this case is -4, -6. So using that zero product property idea, I'm looking for what makes this parenthesis work out to 0, which is -4, and then whatever I see here at the end, which is -6, that's where my vertex is going to come from. Now, getting our x-intercepts is going to require a little bit of math, because like we said, for x-intercepts, the y value is always 0. So I'm going to take my equation and I'm going to plug in 0 for y. That's a -6. And then I have to solve for x. So this is using like old school algebra. So I'm going to add my 6 to the other side. So +6 + 6. I get 6 equals x plus 4 squared. Now I have to get rid of that squared, which, if you recall, we said uses a square root. Now I am not going to do any math with this. I'm just going to leave that as is. I don't want a decimal because it does say exact answers, and technically a decimal isn't exact. The square root, though, is. Now, whenever you take the square root of a number, you do have to put this plus or minus out front, because technically I could take two positive numbers to multiply to make 6, or I could take two negative numbers to multiply to make 6, because the square root just says two numbers that are exactly the same that multiply to make that particular number. So for example, like the square root of 25 could be 5, because 5 times 5 is 25, but it also could be -5, because -5 times -5 is also 25. So that's why we put a plus or minus out front, is to reference the fact that there's two different ways to get the answer. Back to our problem at hand here, we need to finish solving for x, so I need to move this 4 to the other side by subtracting. Running out of space here, so subtracting the 4 from both sides, I get -4 plus or minus the square root of 6. So my two actual answers would be -4 plus the square root of 6 is one of my x-intercepts, and -4 minus the square root of 6 is my other x-intercept. So it says to make a sketch and then check your sketch with Desmos. Now, I think to make a sketch, it makes it a lot easier to find out what these numbers are as a decimal approximation, just because it's a little bit easier to know what I'm talking about then. So if I go into my calculator here, I can type them in. So -4 plus, and then a little hint to make the square root symbol, you don't actually have to type in it or find it. You can type in SQRT and it'll make a square root symbol for you. So -4 plus the square root of 6 is -1.55. And -4 minus the square root of 6 is -6.45, which is exactly what we saw when we were looking at the graph. Okay. Then it says to find the vertex. When I'm looking at the parabola, it's easy to see. However, we can use algebra to find where that vertex would be without graphing. Now, we said the vertex is always exactly halfway in between our x-intercepts. So there's actually a little trick for this. Whenever we're looking for something that's exactly halfway in between, you can use an average. So knowing that my two x-intercepts are at -1.55 and -6.45, I can take the average of those two numbers. Now, if you remember, finding the average or the mean means you're going to add your numbers together and then divide by the number of numbers, in this case, 2. So I'm going to do this in my calculator. So make a fraction first. So -1.55 plus -6.45, and I'm going to do that over 2. It works out to -4. So what that's telling me is that the x value of my vertex, or the middle of my parabola, is at -4, which we already saw. But we're going to use that now to algebraically find our y value. So we're saying that the x value of our vertex is -4. I can then plug it into my equation and get out my y value. So -4 plus 4 squared minus 6. -4 plus 4 is 0 squared minus 6, which is -6. So that's where that comes from. And then our two x-intercepts, just to kind of keep my page going here, were -4 plus or minus the square root of 6. Okay. And then we could make our sketch. Now 100 leads us into a brand new idea that we haven't really worked with before. They do have a student e-tool in here for you to use tiles. If you'd like to use the physical tiles, you're welcome to. However, I do need you to be very careful about cleaning them all up when you're done. So Jessica was at home struggling with her algebra homework. She had missed class and did not understand this new method called completing the square. She was supposed to use it to change y equals x squared plus 8x plus 10 into graphing form. So into that form where it's x plus or minus something squared plus or minus a number at the end. And then her precocious younger sister, who was playing with algebra tiles, said, "Hey, I bet I know what they mean." Anita's algebra class had been using tiles to multiply and factor binomials. So you can explore this, like I said, using the e-tool if you want, otherwise the physical tiles. Anita explained, x squared plus 8x plus 10 would look like this. And she pulled out a bunch of tiles. Now, I do have the digital tiles up just in case, so I can use them to kind of reference things. "Yes," said Jessica, "I'm taking Algebra 2, remember?" Anita continued, "And you need to make it into a square." So that's the important part of this, is a square. Keep in mind, squares have sides that are exactly the same. Meaning, if my square has 5 tiles in one direction, it has to have 5 tiles in the other direction. "Okay," said Jessica. She arranged her tiles on the equation mat as shown at right. So she took her tiles and put them into a little pile here, making it a square. So as she organized this into the square, she noticed something, though. She noticed that she only had 10 tiles for the little corner piece that I'm filling in right now, but she actually needs a total of 16 because it's 4 tiles long by 4 tiles wide. So it says, "Oh," said Jessica, "I need 16 small unit tiles to fill in the corner." "But you only have 10, Anita reminded her. "Right, I only have 10, Jessica replied. She drew the outline of the whole square and said, "Oh, I get it. To complete the square," which, by the way, is what this was called, completing the square, "I need to add 6 tiles to each side of the equation." So we're going to end up adding 6 unit tiles to each side. So now that I've got my 6 unit tiles here that I'm adding on to each side, now I can go through and actually fill out the rest of this square. And yes, I know mine isn't perfect. It's a little hard to do this with just a mouse, but it is a square. So our equation started with y equals x squared plus 8x plus 10, but now we can actually rewrite our equation using what we see here. So we see x plus 4 squared, and that's the same thing as what our y value was if we were to add 6 to it. So we're showing that our equation is the same thing as this. Now we can convert this to graphing form by subtracting the 6 to the other side. So we end up with, and I'm just going to flip-flop my two sides just to make it a little bit more normal looking for us, x plus 4 squared minus 6. Now we can go through and use Desmos to verify this, because we can just plug them both in and show that the two equations are the same. So that's what we're looking for, is if I type these two equations into Desmos, do I get the same picture? And I'll let you type them in to figure that out. But if we move on to number 101, they're asking us to do the exact same thing. So we're going to be completing the square. Now I'm going to use a generic square here. I know we call it like a generic rectangle, but I want to be clear, it is a square, meaning the sides have to be the same. But we're going to set it up in a very similar fashion. So our x squared piece always goes in the upper left. And what we're saying when we complete the square is that these 6 tiles matter more than anything else. I need to organize these 6 tiles into a square, meaning only half of the tiles can go in each of these 2 boxes. So 3 of my 6 x's can go there, and 3 of my 6 x's can go there. Now I'm going to ignore this bottom corner box for a moment. Notice it's still blank. I didn't write anything in there. Now, in order to finish this box, I would have x and x, 3 and 3. But that would cause me to get 9 tiles down here. But I only had 7 tiles to work with, so I actually have to add in 2 tiles in order to fill this box in correctly. So I would write this as x plus 3 squared minus those 2 tiles that I had to add in order to make it work. So that means the vertex of my parabola is at -3, -2, because it's always opposite of what we see here, -3, and exactly what we see there, -2. To find my x-intercepts, we said we plug in 0 for y and solve for x. So I would draw my line, add my 2 to the other side first. Take the square root. Don't forget the plus or minus out front of that. And then subtract the 3 to the other side. So my 2 x-intercepts would be at -3 plus the square root of 2, 0, and -3 minus the square root of 2, 0. I'm going to go through that all again. So, like I said, I use a generic square when I do this, but if you want to use the tiles, that works too. So just like before, our x squared piece always goes in the upper left. We're going to ignore that 11 for a minute. Just looking at this 4, like we said, we need to split it up evenly into these 2 side boxes in order to make it a square. So half of 4 is 2, so I'm going to put 2 x's in each side. Again, ignoring this bottom corner box, which is still blank. I'm going to fill out the sides of the box. And that would force me to get 4 tiles here. but I actually needed 11. So I actually have like 7 extra little tiles sitting out off to the side. So how I would write that is y equals x plus 2 squared plus 7 extra little tiles. So my vertex is at -2, 7. And then I can solve for my x-intercept. So I plug in 0 for y and solve for x. And I'm just following the exact same process I did before. But I run into a little bit of a snag here. This one, if I try and type this into my calculator, the square root of -7, it doesn't work. So this one doesn't actually have x-intercepts, so we would just say none. And you can check that if you wanted to. Like if you go over to Desmos and graph this parabola, so it was x squared plus 4x plus 11, you'll see it doesn't actually cross the x-axis at all. So it's okay that that when we try and find our x-intercepts, we don't find any because it doesn't have any. That happens sometimes. Moving on to 102. So help Jessica with a new problem. She needs to complete the square to write x squared plus 4x plus 9 in graphing form. So if I make my generic square or my tiles, whichever works better in your brain, the x squared always goes in the upper left. I take these 4 x's and split them up evenly into the 2 side boxes. And then ignoring the bottom corner, I figure out what the sides would be, which gives me a 4 down here. But I needed 9, so I have 5 of those tiles just hanging out off to the side because they don't fit in the box. So my completed, or my graphing form of this parabola would be x plus 2 squared plus those 5 extra tiles. So this is my graphing form for part A. I'm going to let you find the vertex and x-intercepts and then see if you can graph the parabola. It asks us to find the y-intercept. Remember that we said y-intercepts are where x equals 0. So in order to solve for part C, what I'm telling you to do is put in a 0 for the x value and get out a y value. Now 103 goes into something a little bit more challenging. It talks about, if you've noticed, if you look back at our problems, every single time so far, this middle number has been even. So dividing it equally into these 2 side boxes was really convenient. 103 talks about, what if it's not even? So this time I have a 5 in the middle instead of a 4 or a 6 or a 2. So it still works. You can still make a square. It's just a lot messier. So what you'll find is that we'll use completing the square pretty regularly. But in general, if we've got an odd number here, we're not generally going to use it that much, just because it does give us some messy numbers. Because 5 would split into 2.5 x's on each side. And if we fill out the sides of the box, what that causes us to get right down here is a 6.25. Again, making our numbers fairly messy. But we only had 2 tiles. So there are 4.25 tiles in here that I had to add on into it. So if I was to write it in graphing form, I would write it as x plus 2.5 squared minus those 4.25 tiles that I added in to fill in this corner of the box. Again, I want you to find the vertex and make a little sketch of the graph. (104) gives you 2 new problems, and it's asking you to find or create graphing form for each of these. State the vertex and x-intercept of the parabola. Now, 104 and 105, just so we're clear, are ones that I would not expect you to be really great at today on your own. These are ones that we'll kind of focus on as we move forward through the rest of the chapter together and stuff. But in case you're curious, in this case, if I was setting up the box, those 10 x's would get split up evenly. You'll notice this time I don't have a last number. So when I set up the box, I get 25 here, but I didn't want anything there. So to write it in graphing form, it would have been x plus 5 squared, and I have to take all 25 of these tiles away, like that. And again, it asks you to find your vertex and x-intercept. This one is even more challenging because not only is this an odd number, but I see a negative out front. That's a lot to deal with. What I teach my Algebra 2 students when they deal with this kind of stuff is anytime there's anything in front of this x squared and we're trying to complete the square, we're just going to pull it out of all of our pieces. So I'm going to kind of like reverse distribute it. See how like if I went negative times x squared, I get negative x squared. Negative 1 times negative 7 will give me positive 7. Negative 1 times negative 2 would give me our positive 2 back. So I just like undid that. Then I'm only going to complete the square on the stuff on the inside. Again, taking that negative 7 and splitting it up evenly into the two side boxes, which gives me negative 3.5 in each of them. Which if you multiply negative 3.5 times negative 3.5, you get 12.25. But I actually needed negative 2 tiles, and I got positive 12.25. So this one is going to look a little bit funky. So it's going to be x minus 3.5 squared, and I have to take away 14.25 because I need to take away all the positive tiles I put in here and 2 more to get into negative 2. Now, I'm not going to give you an answer here on 105 because I do want you to see if you can figure it out for yourself. But like I said, this is one of those things we're going to spend some time on together as we move forward with the rest of the chapter. So we're just looking for, is there a way for us to take any generic equation, like they're using B and C to represent any number, and rewrite it so that it's x plus or minus something squared plus or minus something. And my hint to you is there is. But we don't know what that looks like just yet.